Hi, my name is Bugihano Marali, and I present a paper on tactile classification of object materials for virtual reality-based robot teleoperation on behalf of Francesca Palermo, Gaspar Altoever, Mauricio Valle, and Ildar Farhadzitov. Recent years have seen a wide adoption of virtual reality technologies in robot teleoperation. VR-based robot teleoperation mostly relies on 3D reconstruction of the remote environment generated by RGBD cameras. Unfortunately, objects' materials can be hard to distinguish in such reconstructions, leading to operator making incorrect decisions. Consider an example. Here, objects present in the remote environment are of different material, but they appear very similar in the operator's VR view. The operator might mistake a piece of metal for styrofoam, and subsequently fail to pick it up with the robot. We suggest using tactile sensing and classification to identify objects' materials and visually communicate those materials to the operator in the VR interface. Our experimental setup consisted of a robot manipulator, an end effector-mounted RGBD camera, virtual reality headset and controllers, and a fiber optics-based tactile sensor. The tactile sensor has 3 pairs of optical fiber cables that use reflected light's intensity to measure the deformation of the finger. The 4th pair of optical fiber cables is used to measure the distance between the tip of the finger and nearby objects. Supervised teleoperation was used to collect tactile data. The operator would set a desired scan position, and robot would perform a scanning motion. This way, we've collected a highly variable dataset that would be representative of real-world robot teleoperation. We have scanned 5 objects of different stiffness and smoothness: metal, styrofoam, paper, silicon, and soft foam. All objects were flat. Each object was scanned 150 times, with a new combination of scan depth and orientation set by the operator every 3 scans. Additional 50 synthetic samples were generated by augmenting existing samples at random, bringing our dataset to 200 samples per object and 1000 in total. The raw tactile data was recorded starting from 2 seconds from before the sensor touches the object until 2 seconds after sensor leaves the object surface. All scans had constant duration, length, and direction with respect to the robot's end effector. We have also recorded the desired scan pose and the robot's end effector trajectory error. We use spectrograms of raw tactile data for objects' material classification. Spectrograms were generated with 52 time segments and 50 spectral bands. You can see that the resulting spectrograms were remarkably visually distinct. We compared 3 classifiers: random forest, convolutional neural network, and multimodal convolutional neural network. The convolutional neural network was trained using spectrograms only. Meanwhile, the random forest and multimodal convolutional neural network were trained using both spectrograms as well as end effector state. We tested and validated our classifier using a 60-20-20 split. The random forest showed highest accuracy of 94%, followed by multimodal neural network at 92%. However, we hypothesized that multimodal neural network will generalize better to changes in scan duration or length. We proposed 2 material visualization methods in VR, as color-coded point clouds and/or Optomap overlay. The scanned object is segmented based on the desired scan location, and the classification result is applied based on the color code shown in the user interface. This concludes our presentation. Please feel free to consult the full paper for details and ask any questions now.